The last thing we're going to talk about in our energy unit is how it relates to power. Power is the rate at which work is done, or the amount of energy over a unit time. Okay, it's a rate. Uh, Work per unit time or energy per unit time. Quick example, the rate at which electrical energy is transferred into heat and light, and a light bulb, that's an example of power. Uh, and formula, in the formula, it looks like this. Power, capital P, is equal to work over time. Work over time, or power is equal to energy over time. Both can be used, and the energy is probably going to be specified in the problem, so they might be talking about the kinetic energy over unit time, or potential energy, or electrical energy, whatever energy they're specifically talking about per unit time. That's power. Uh, and units, uh, well, energy or work is a unit of J for joules per time seconds. So joules per second is power, and a joule per second is a what we call a watt. W-A-T-T. Watt. Uh, Most people generally use W for watt. Uh, I'll add a couple of lines at the top to kind of distinguish it from work, just so it doesn't get confused with work. But the units for power is watt, uh, and that comes from joules per second. Power is required to move an object with a constant force at a constant speed. Okay. Uh, for example, the power necessary to move a vehicle at a constant speed is measured in horsepower. And a horsepower is a unit of power. 1 horsepower is equivalent to 746 watts. An example problem for power asks how much power does it take to raise an object that weighs 200 newtons a distance of 10 meters in 25 seconds. So uh, we have a situation where we need to figure out the work to lift this weight this distance. So work is equal to force times distance, or displacement. Let's write it the way I normally plugging in our numbers. We have 20 newtons. I'm sorry, 200 newtons times 10 meters is 2,000 joules. That's our work. And to get power, power equals work over time. Work is 2,000 joules, so 2,000 over time is 25 seconds. 2,000 joules per 25 seconds is equal to 80 watts. The next example problem is a little more involved. And we've got 25 kilonewton car. It's going to be accelerated from 0 to 100 kilometers per hour in 10 seconds. We're going to neglect all the frictional losses and determine how much power must be supplied in this during this process. Uh, so we've got 25 kilonewton car uh, going from 0 to 100 kilometers per hour in 10 seconds. What you have here is a situation where you can figure out the change in kinetic energy. We can assume the change in potential energy is zero because it's, on the ground and it's going from one spot, here's the car, to another. Choose a different color for the car. Here's the car. Car. It's going to go from one spot to another. So you can see potential. If we call this our zero potential energy line, there's no change in energy. Change in kinetic energy, or change in kinetic energy can be found because we know it's going from 0 to 100. So change in kinetic energy, which work is the change in kinetic energy, we've got kinetic energy final minus kinetic energy initial. So what we have is a situation where, hey, the initial velocity is 0. The initial velocity is 0. So our initial kinetic energy is also 0. So work is essentially going to be equal to whatever our final kinetic energy for this problem. Again, if it was starting from a velocity, things would be different. But since we're starting at 0, we can say work is equal to final kinetic energy. A couple of things we need to take care of is we've got 100 kilometers per hour. We need to convert that to meters per second. And we have a 25 kilonewton car. That's the car's weight. That's force weight. We're going to need to figure out, well, number one, we'll have to convert that to newtons and also figure out what its mass is. So that's going to be mass times gravity. So 100 kilometers per hour times our conversion rate is 1,000 meters per kilometer, or 10 to the third meters per kilometer, times 1 hour per 3,600 seconds is 27.8 meters per second. 25 kilonewtons is 25,000 newtons equals mg. Divide both sides by gravity, acceleration due to gravity, which is 9.81, and you get a mass equal to 2,550 kilograms. And so these are the numbers we're going to be able to use in our kinetic energy formula to figure out work. And we're going to figure out work so that we can figure out the power using the amount of time that this car is accelerated. Work equals mass times velocity squared over 2. Our mass is 2,500. Let's pick up where I left off. So we've got work equals mass times velocity squared over 2. The mass is 2,550 kilograms. Velocity is 27.8, and we're going to square that and divide everything by 2. And we will get 9.85 times 10 to the 5th joules. And we plug that into our power equation. Power is equal to work over time, or work per unit of time. So our new power, we plug in 9.85 times 10 to the 5th for work. Our time is 10 seconds, and therefore power is equal to 9.85 times 10 to the 4th watts, which is equivalent to 98.5 kilowatts.